Welcome to section 12.5. In this section, we're going to be looking at some more objects in the third dimension, specifically lines and planes. So we're going to start off talking about the equation of a line. So traditionally in algebra, when we think of the equation of a line, we usually think of something of the form y equals mx plus b, right? Where m represents the slope and b represents the y-intercept. When we transition into 3D, the equation of the line has to adjust slightly in order to accommodate the fact that we are in the third dimension. But the general form of it is going to look fairly similar, and we're going to point out the similarities in just a minute. But as you can see, I've already got a diagram up here for us to look at, and I've already got the labels up there. So let's talk about what these labels mean. So first off, we have this vector r0 right here. That is the position vector of a point p0. That point p0 there on the line. So this blue line right here, this is the line in question. So we have r0 is the position vector of that point p0. Then we have the position vector of the point p. That's r right here. So that's the vector r. Then we create a vector parallel to the line. So that would be right down here. So that's the vector v. That is a position vector, right, coming out of the origin that is parallel to the line in question. And then lastly, we have the vector that is created between the 2 points on the line, so p0 and p. And that's going to be our vector A, we will call it. And again, that is the vector p0, p. Now, how do we use this to develop the equation of the line? Well, we can use vector addition. So if we look at the vector r, so if we start with r, the vector r starts at the origin and ends at p, like that. Notice if we take r0 plus a, they start at the origin and end at p, just like r does. So r, we can say, is equal to r0 plus a. Okay, so this is true because of the properties of vector addition. But we don't necessarily want to use a because that value is dependent upon these points on the line. We want to use the general vector v, which is the same direction as a, right? They are parallel because v is parallel to the line and a is on the line. So since a is parallel to v, we say that a is equal to tv. So that's t times v for some scalar t. Thus, we get r equals r0 plus tv. And this formula is known as the vector equation of a line. So r equals r0 plus tv. And t is what we call the parameter. Okay, so t is a scalar, and as t changes, we move up and down the line and plot different points. Now, of course, all these components here, these are vectors. These are not just numbers or variables like we thought of them back in algebra. But if we reorganize this a little bit, so put r equals vt plus r0. So just for the sake of argument, this is the formula we're going to use, but I'm going to rearrange them a little bit here just so we can see kind of the side-by-side. So when we talk about the slope of a line in algebra, the slope is telling us what direction to go, right? It tells us the direction the line is pointed. In 3D, this one, v, that is our direction vector. So this one is giving us direction. In other words, the slope. Okay, now we can't call it slope in 3D because slope implies that you're just moving between left and right. So we do have a three-dimensional space that we're working in, but the v basically acts like the m. So these two are kind of corresponding. X and t are going to be the values that change. So you put in x, you get out a y. You put in a t, you get out an r vector. And then this r naught over here, the y-intercept back in algebra, this y-intercept, it's the vertical intercept. We use it as kind of like a starting point or an initial point or an initial value. That's what r naught is. So r naught is just the vector that points to p naught. That says when you're tracing the line, start here and go that direction. That's basically what this is doing. So this is like our initial value. Just like b, that y-intercept, gives us a starting point, right, or an initial value to go off of. So hopefully you can kind of see the similarities between the equation of the line that we know and the new vector equation of the line that we're going to work with in 3-space. Now, if we want to expand this out a little bit so we can actually look at the components of these vectors, so we get r is xyz, r naught is x naught, y naught, z naught, plus t times the components of v, we're going to call them a, b, and c. So if we distribute that t in there, we get x naught, y naught, z naught, plus ta, tb, tc. And if we go ahead and combine these across the addition here, that gives us x naught plus, I'm going to put the a first, plus at, y naught plus bt, and z naught plus ct. Now, by setting it up this way in these component forms, we know that in vectors, the corresponding components must be equal. So we know that if xyz is equal to this, then the first component must be equal to this first component, the second must equal the second, and the third must equal the third. So that gives us what we call the parametric equations of a line. So the parametric equations of the line come from setting these components equal. So x equals x naught plus at, y equals y naught plus bt, z equals z naught plus ct. These are the parametric equations of the line, because we now have a set of equations that give us each component, and it's all in terms of that parameter t, that t value that is changing from point to point along the line. Now, from the parametric equations, they do all have t inside of them, so if we wanted to, or needed to, we could solve each of these for that value of t. So like this first one, we would subtract the x naught to the other side and then divide away the a. So if we did that, we would get t equals x minus x naught over a. If we did it for this equation, we would get t equals y minus y naught over b. And if we did it for this one, we would get t equals z minus z naught over c. And these are going to form the symmetric equations of a line because each of these fractions are equal to t, which means they must be equal to each other. So this is how we get rid of the parameter t if we want to do that. So the symmetric equations of the line, we take all these values that are equal to t and instead set them all equal to each other. So there we have the symmetric equations of a line. All three of these forms, so the vector equation of the line, the parametric equations of a line, and the symmetric equations of a line, all of these are interchangeable. You can get to one from any of the others using the methods we just talked about. So if you have the vector equation of a line, you can put it in component form and then split it up, and that'll give you the parametric form. If you want to go backwards, recombine those into that vector, and you can put it back in this form. If you want to get the symmetric, do what we just did here. So solve for t and then combine together, or undo that process to go back to the parametric equations. So all of them are interchangeable, and you need to be familiar with all three versions depending on what the questions are asking of you. So let's take a look at an example. Find a vector equation and parametric equations for the line that passes through the point 513 and is parallel to the vector I plus 4j minus 2k, and then find two other points on the line. So for part A, so we'll start off with the vector equation. The point 513, that gives us like our starting point or our initial point. So that'll be the R naught vector. So vector 513 plus t times the direction vector for the line. We know that it's parallel to this vector, which means, in other words, they have the same direction. So that one, it'll be 1, 4, negative 2. So we have our position vector, we have our direction vector. This is the vector equation of that line. And then the parametric equations, we're going to get x equals, y equals, and z equals. So we get 5 plus 1 times t, so 5 plus t. We get 1 plus t times 4, so 1 plus 4t. And 3 plus t times negative 2, so that's 3 minus 2t. So this up here is the vector equation of the line. And these are the parametric equations of the line. And then for part B, it says find two other points on the line. So all we need to do to find other points is to start changing up the value of the parameter. So if the parameter is 0 and we plug that in, that gives us 513, which is our starting point, right? So that corresponds to the value of t equals 0. If we let t be anything else, we will get new points out of this. So choose different parameter values. And it does not specify what values, it just says two other points. There are infinitely many other points on this line. So let's take t equals 1. So that would give us, you can use either version of this, like plug in the 1 right here and then just add the vectors. Or you can plug in the 1 into the 3 components and add it together. I'll do it with the vector here first. So that would be 513 plus 1 times 1, 4, negative 2. So that's 6, 5, and 1. So the point 6, 5, 1 is also on this line. If we took t equals negative 1, for example, it could be anything, but I'll just pick negative 1. And let me plug it into this one this time. We get 5 minus 1 is 4. 1 minus 4 is negative 3. 3 plus 2 is 5. So we end up getting 4, negative 3, 5. And that is another point on the line. And again, those were not the only choices. You had infinitely many different choices for different values of t. These are just a couple of the easier ones. Let's take a look at another example. Find parametric equations and symmetric equations of the line that passes through the points A and B given here, and then at what point does the line intersect the xy plane? So to find the equations for this line between the points, we need two things. We need a position vector and a direction vector. The position vector comes from a point on the line, so we've got a couple to choose from, so that's fine. The direction vector has to be a vector that points the same direction as the line, or is parallel to the line, or is on the line. So to do that, all we have to go off of are these 2 points, but we can create a vector between any 2 points that we want. So we're going to create the vector AB, and hopefully you remember how to do that, but you take terminal minus initial. So we're going to get 3 minus 2, comma, negative 1 minus 4, comma, 1 minus negative 3. So that's 1, negative 5, 4. That will be our direction vector. And our position vector, you can pick either point, but since I used A as the initial point here, I'll go ahead and just use A. So that'll be 2, 4, negative 3. Now for the parametric equations, so we're going to need our x equals, y equals, and z equals. And remember, in this formula right here, x naught, y naught, and z naught come from the position vector r naught, and a, b, and c come from the direction vector v. So we get 2 plus 1t. We get 4 minus 5t, and we get negative 3 plus 4t, and those are the parametric equations. Then to get the symmetric equations, you can think about it in 2 ways. So you can go ahead and do the subtraction, right? Solve for t, so subtract and divide everywhere that you need to. Or if you just remember the general form here. So again, you get x naught, y naught, z naught from the r naught. You get a, b, c from the direction vector v. So this one, when we do that, we end up getting x minus 2. Technically it's over 1, but you don't really need to put over 1, equals y minus 4 over negative 5 equals z plus 3 over 4. And those would be the symmetric equations of the line. And then for part B, at what point does the line intersect the xy plane? Now, when we say intersect the xy plane, what is true about every point that lies on the xy plane in terms of 3D and 3 space? all of these points in the xy plane have a z value of 0. That is what they all have in common. So really, this is just asking us, let z be equal to 0. And then from here, we can solve to find x and y, and that'll give us the point in question. You can use either the parametric equations or the symmetric equations to solve it. It does not matter. If you use parametric, you would plug z equals 0 into here and then solve for t, and then plug that into both. Or if you go over here, plug in 0 for z here, and then separate this into two different equations. That ends up giving us, so we get x is 11 over 4, and y is 1 over 4. So our point on the xy plane, where this line crosses through it, is 11/4, 1/4, 0. So again, just substitute z equals 0 into either the parametric or the symmetric, and then solve the rest for x and y, and you'll get the same result. Now, there's a little note down here right below this problem. This is a note that we're not really going to use right now, but we're going to be using it quite a bit in the last chapter of the course. So this is something that there's not really any better place to put it than the section on lines, but we're not going to see this too much until way later. Don't worry, I will remind you again once we get into that last chapter about this formula, but we're just putting it here, kind of plant the idea in your head that this formula exists, and we will come back and deal with it much more extensively in the future. So note, the line segment from R0 to R1 is given by a formula in terms of t. R of t equals 1 minus t R0 plus t times R1. So this formula we will end up using a lot more down the road. But basically, as you go from R0 to R1, if t starts at 0, then we would end up getting, right, R0 plus nothing. So we start at R0 when t is 0. And then when t goes up to 1, this one becomes a 0, and we're left with R1. So this we end up getting for t going from 0 to 1. And that would be how we could create the equation of a line segment. So not the whole line, just a piece of it. But again, we'll look more at that later on. This next example here, we want to show that the lines L1 and L2 are skew. So first, we have to define what that means for lines to be skew. Now, in 2D, when you're looking at like the XY plane like this, lines can be parallel. They can go the same direction. They could cross and intersect at a point, and that's it. Those are the only possible choices in 2D, right? They can either meet somewhere or they have to be parallel. In 3D, that is not the case. In 3D, you can have lines that are parallel, like that, and that's no problem. You can have lines that intersect each other, like that. Again, no problem. However, there is a third case in 3D. You can have a line going like this and a line maybe going like this. So like this one is going this way and this one is like under it and it goes like off that way and then like that way. So kind of, one of them is like coming out of the screen at us and another one is down here, like passing under it, something like that. These lines are not parallel, right? They do not point the same direction, but they do not meet. They do not intersect anywhere because they're like on different planes, essentially. Because we're working in 3D, those are skew lines in 3D. So when we say skew, we mean not parallel and do not intersect. All right. So skew, the test for skew is basically a process of elimination for the other two conditions. So we want to see if the lines are parallel and then see if the lines intersect. And if the answer to both of those questions is no, then by default the lines are skew. So we're going to start off, try to color code this a little bit. So we'll start off with parallel. To determine if two lines are parallel, we just need to look at their direction vectors. So we'll take a look at the direction vectors from L1 and L2. So again, those are the coefficients on the parameter. So that's going to be 1, 3, -1, and 2, 1, 4. And then we have a couple different ways to determine if they're parallel. The first that we saw in the other section is you can use the cross product. And we could observe whether or not the cross product is 0. If the cross product is 0, they are parallel. If it's not, then they're not. So we could use cross product. There is another way that is can generally be a little bit simpler. So OR, and that is the method of scalar multiples. If the vectors are pointed the same direction, they don't have to be the same vector. They can have different lengths, right? You can have a vector that's pointed like this and a vector that's pointed like this. These are still parallel, even though they're not exactly the same vector. They have the same direction. What we can do is we can try to determine if one of these vectors is a scalar multiple of the other. Okay, so like if we look at, 1, 3, -1, and 2, 1, 4. In order for these to be parallel, the first component is doubled. So if this vector is truly a multiple of this one, it should be doubled the whole way. That would be 2, 6, -2, like that. However, the second component here has been multiplied by a third, right? It's been cut in a third, which does not match that same relationship. And then our third component here, the third component goes from -1 to 4, so this one is times -4. So clearly the ratio here is not the same for all of these. And we can see then that these vectors must not be parallel. So move this up a 10. So not parallel. So these ones are not parallel. And again, if you like to use the cross product instead, just take the cross product, show that it's not 0, and you'll get the same result. It's a little more systematic that way. And then the follow-up, do they intersect? In order to determine if they intersect, we have to see if they have any points in common. Or in other words, is there a point that makes them equal? So we're going to equate. So we're going to set the x is equal, the y is equal, and the z is equal to each other. So we're going to get 1 plus t equals 2s, -2 plus 3t equals 3 plus s. And 4 minus t equals negative 3 plus 4s. So now we need to solve this system of equations here, these three equations, for t and s in any way that we can. So let me do a little bit of this here. So like for this one, we could solve t equals 2s minus 1. We could then take this and put it in this equation to find t. Or excuse me, to then solve for s, like replace it with t to find s. So we would get negative 2 plus 3 times 2s minus 1 equals 3 plus s. That would give us an s value of 8 over 5. And then this value goes back in there to find t. So we end up getting t is 11 over 5. And obviously I'm kind of glossing over the algebra a little bit because this is just algebra stuff. And then for the last one, we now have values of t and s, so we would substitute those in. So we get 4 minus 11 over 5. And we're wondering, is that equal to negative 3 plus 4 times 8 over 5? It turns out, if we keep going through the work, that they are not equal. So they do not intersect. Okay? Because the only chance they had of intersecting was if these were the values of s and t, right? Those are the only values that make these equations work. But those values made the third one not work. And those were our only choices, which means that there are no points that make this work. So there are no points where they meet. They do not intersect. So we can say, so therefore, L1 and L2 are skew. Again, because they are not parallel and they do not intersect, they must be skew. Now, let's go ahead and move on from lines and start talking planes. So a plane is determined by a point, P naught, okay, so that's x naught, y naught, z naught, in the plane, and a vector n that is orthogonal to the plane. Remember, that means perpendicular. We call n the normal vector. So we use a point in the plane and the normal vector. These are the two things that we need to find the equation of a plane. So because if we're trying to use vectors like in the plane, so if we have a plane here and like the vectors can be pointed any number of different ways, and that doesn't give us clarity on the plane. What does give us clarity is a unique vector pointed basically straight out of the plane. That's where this orthogonal normal vector comes into play. And as the plane would move and change, the normal vector would change with it. And so we can use that to identify the plane more clearly. So first we're going to look at deriving this using vectors, and then we'll see what the real kind of fully fledged out version of the equation is that we're going to use. So P is a point in the plane with R naught and R, position vectors of those points P naught and P. Then the vector P naught P is equivalent to R minus R naught. And so right here I have a little diagram for us to look at to help with the visual of this. So here's R naught pointed to P naught, R pointed to P, and this vector between P naught and P is R minus R naught. The reason that that's true is because of, again, the vector addition. r starts at the origin and ends at P, so does r naught plus this one. So if we want this one to make the equation true, it has to be r minus r naught, because then the result would give us an r equals r, and everything equates out. So how do we set up an equation? Well, we know that the normal vector, so n, you can see I've got it kind of sticking out right here from the plane. The normal vector is orthogonal to the plane. So n is orthogonal. Since it's orthogonal to the plane, it is orthogonal to all vectors in the plane. So if we want to run a test to see whether two vectors are orthogonal or not, we can use the dot product. What we're doing here is we know that n is orthogonal to every vector in this plane, so the dot product of n with any vector in this plane must be 0. And we'll take the vector, this orange one here, that r minus r naught equals 0. This is our kind of key fact right here. So since the normal vector is orthogonal to the plane, it's orthogonal to everything in the plane. That includes this vector. So their dot product has to be 0, again, because they are orthogonal. Another way of writing this, and this is kind of the more formalized version of this equation, if you distribute the dot product, which you can do, and then add that term over there, we get, so similarly, we get n dot r equals n dot r naught. This is the vector equation of a plane. Now, this version of the planar equation is not the one that we're really going to use. The one that we're going to use stems out of this one. And what we're going to do is we're going to bring in the components of these pieces. So the normal vector n, so that normal vector n, its components we call a, b, and c. And the vector r minus r naught, well, r was corresponding to x, y, z. R naught corresponds to x naught, y naught, z naught. So that's x minus x naught, y minus y naught, z minus z naught. So if we take those, put them in this form, so we get ABC dotted with x minus x naught, y minus y naught, z minus z naught equals 0. And then perform the dot product. So the dot product, right, you need to multiply the corresponding components and then add everything together. So we're going to get A times x minus x naught plus B times y minus y naught plus C times z minus z naught equals 0. And this is what we call the scalar equation of the plane. This is the one that we're going to be using. Okay, so this is the one that we're going to use a lot because it's already set up in such a way that if you know the point on the plane, that's x naught, y naught, z naught, and you know the normal vector, that's a, b, and c, you have all the pieces you need in order to get the equation. Okay? So again, two things you need to get the equation of a plane. You need a point on the plane and a normal vector, a vector that's orthogonal to the plane. Let's take a look at some examples. Find an equation of the plane through the point 2, 4, -1 with normal vector 2, 3, 4. Find the intercepts and sketch the plane. So in terms of the equation, again, we need a point on the plane, given, and we need the normal vector, given. So this one's a little bit of a freebie. Just kind of give us all the pieces that we need. So we're going to get 2 times x minus 2 plus 3 times y minus 4 plus 4 times z minus -1 equals 0. And the way that we want to get our answers here for the equations of the planes, we want to put them into standard form, which is where we're going to have all the variables on one side and move all the constants to the other. So let's expand this out. So 2x minus 4 plus 3y minus 12 plus 4z plus 4 equals 0. So we're going to get, 2x, 3y, and 4z will stay over here. Everything else is going to go over there. So we have -4 and 4, so they cancel. -12, add it over, that's 12. So and this is standard form. So this is often how we will write our solutions for the equations of planes. We put them in standard form so we can see all the variables together and move all the constants over to the other side. Now, it asked us to find the intercepts of the plane. So in order to find the intercepts, we're going to have some zeros in here. So the x-intercept, this is where we are on the x-axis, which means that y and z are both going to be 0. So for the x-intercept, we let y be 0 and z be 0. We have 2x equals 12, so x is 6. So we get 6, 0, 0. The y-intercept is where x and z are 0. So we're on the y-axis. We get y is 4. And z-intercept, we're on the z-axis, so x and y are nothing. We end up getting z equals 3, so 0, 0, 3. And we can use those to draw out the plane. So when it comes to plotting planes, they're kind of hard to visualize when they're out in space, and they do extend infinitely in all directions, but it is very helpful to plot them on like the coordinate axes just for the sake of visibility. So we have x, y, and z. So we go 1, 2, 3, 4, 5, 6. 1, 2, 3, 4. 1, 2, 3. So let me just plot these points right there. And we'll just connect the dots. And that is a sketch of our plane. Okay, this is just the portion that lies in the first octant. So that's the portion that's up in front of the axes here where we are looking down on it. Again, it does extend infinitely in all directions, but that makes for kind of a boring drawing because then it's all just one big, like sheet of paper, one big flat object. But this gives us an idea of kind of how it's like turning, how it's sloping, what direction it looks like it's headed. So this gives us a pretty good idea of what the plane looks like just within a smaller portion of the graph. All right, let's take a look at another example where they don't give us all the information right out of the gate. So find an equation of the plane that passes through the points P, Q, and R, given here. So remember, in order to find the equation of a plane, we need a point on the plane. We have an overabundance of those. We also need a normal vector, that is a vector orthogonal to the plane. We don't have one of those, right? All we have right now are points in the plane. So we need to think about methods for how we can get a vector that is orthogonal to all of the points here. Now, you can't take the points themselves and try to like determine orthogonality, because if I just have a point here, like this vector, you'd be like, oh, it's orthogonal, but what about this one? It's orthogonal. What about this one? It's orthogonal. Like that doesn't work for points. It has to be vectors that we're working with. So what we're going to do is we're going to create some vectors. We're going to create vectors between these points. There's a few different choices. I'm just going to kind of go in alphabetical here. So PQ, again, terminal minus initial. So we get 3 minus 1 is 2. Negative 1 minus 3 is negative 4. 6 minus 2 is 4. And then PR. So we go 5 minus 1 is 4. 2 minus 3 is negative 1. 0 minus 2 is negative 2. You could have picked QR. It doesn't matter. So these vectors lie in a plane. Okay, so we've got a plane. We've got these two vectors that lie in it. If we want to create a normal vector that goes like up and out, it needs to be orthogonal to both of these vectors that we just created. And we do have a way of finding vectors or creating vectors that are orthogonal to two others, and that is the cross product. So our normal vector is going to be the cross of PQ with PR. So remember, the cross product produces a new vector that is orthogonal to both of the ones that went into it. And that's exactly what we need. So we set up our I, J, and K. We get 2, negative 4, 4. 4, negative 1, negative 2. And if you run the computation on that cross product, we end up getting 12I plus 20J plus 14K. And that gives us our normal vector. So normal vector is right here. And for the equation of the plane, we need the normal vector and a point. We can choose any. I'm just going to pick the first one just because it's the first one. But you could pick any of the points. And we're going to get, so it's A times X minus X naught plus B times Y minus Y naught plus C times Z minus Z naught equals 0. So A, B, and C come from the normal vector. X naught, Y naught, Z naught come from the point. So we have 12 times X minus 1 plus 20 times Y minus 3 plus 14 times Z minus 2 equals 0. We can simplify this a little bit even before we start moving stuff around. Notice there's a common factor of 2 in all of those. We can divide it away. And then we can go ahead and distribute the 6, the 10, and the 7, bring all the variables to one side, the constants to the other. So we end up with 6x plus 10y plus 7z equals, that's negative 6, negative 30, and negative 14. Add all those together to the other side, we end up getting 50. And a pretty common question that we get at this point is, what if I had switched these around? What if I had switched those vectors around? Well, if that was the case, remember the cross product is not the same when you switch the order, right? A cross B equals the opposite of B cross A. When it comes to normal vectors, though, it's okay to switch them like that, because if you have a normal vector pointed up like this, the opposite vector going down this way is still a normal vector. It's still orthogonal to this plane. It's just pointed the opposite direction, and so that would be okay. This is why they say find an equation of the plane, not necessarily the equation of the plane, because there's different kind of variations on this equation. They're all equivalent, but they might look slightly different depending on what numbers you got, what direction your normal vector is pointed. But you can potentially switch those around and still get a valid answer. Now, to finish us up on this section, I know it's been a long one, we're going to look at the relationship between lines and planes a little bit, so kind of combine all of this together. Two planes are parallel if their normal vectors are parallel. Okay, so the relationship that the planes have with each other is the same as the relationship between the normal vectors. This makes it a lot easier on us because now we don't have to look at all of the infinite dimensions of these planes to see if they're orthogonal or parallel to each other. We just have to look at two vectors, the normal vector of the first plane, the normal vector of the second plane. If they are parallel, so are the planes. If they're not, then the planes are not. Okay. If they are not parallel, then they intersect in a straight line. And the angle between the two planes is defined as the acute angle between their normal vectors. So the angle between the vectors is the same as the angle between the planes. So let's take a look at an example, kind of use this same idea here. Find the angle between these two planes, and then find symmetric equations for their line of intersection. All right, so we have the equations of the planes, so we actually do know their normal vectors because we know how to find the normal vector from the equation. Remember, the normal vector, that's the a, b, c. So those are the coefficients on x, y, and z in both of these equations. So for this first one, that's going to be 1, 1, 1. For the second one, we get 1, negative 2, 3. So now, if we find the angle between these two vectors, that will be the angle between the planes also. How do we find the angle between two vectors? Well, we have some different formulas for it. I think the first one that we really looked at was the dot product formula. So this is n1 dotted with n2 equals magnitude of n1 times magnitude of n2 times cosine of theta, where theta is the angle between them. So we're going to get cosine of theta is, let's see, we divide this under here. So we're going to have n1 dotted with n2 over length of n1 times length of n2. Take the dot of these, you get 1 plus negative 2 plus 3. So 1 plus negative 2 plus 3 over, remember how to find the length of a vector? You take the square root of the sum of the components squared, like that. So for the first one, for n1, we get the square root of 1 squared plus 1 squared plus 1 squared. So that's radical 3 times square root of 1 plus 4 plus 9. So that's square root of 14. So we end up with 2 over rad 42. That's not the answer yet. That's just the cosine of theta. If we want theta itself, we need to take the inverse cosine. So theta will be inverse cosine of 2 over rad 42. And if you were looking for an exact value with no rounding whatsoever, that would be the value. This is as exact and accurate as we can get. But if we want to understand kind of what that means numerically, in terms of radians, this is 1.257 radians, or about 72 degrees. So we're looking a little bit less than 90 degrees. Okay, so 72 degrees is the angle between the two planes, which of course means they're not parallel. Since they're not parallel, they must have a line of intersection for the planes. So we need to find the equation of that line. Okay, so what we have here, let me go ahead and let me just draw this in here. So we have one plane up here, another plane up here, they intersect, so they cross through each other. Like that. They have normal vectors. So that'll be like n1 and n2. Right? So the normal vectors, right, have the same angle between them as the planes do as well. So the line in question, this is the line of intersection. And again, this doesn't stop in my drawing. Like, it does extend infinitely in both directions. So this will be our line L right here. So we need, in order to get the equation of this line, we're going to need a point on the line so that we can get a position vector, and we're going to need the direction vector for the line. Okay, so let me separate this off here. So we're in part B now. So we need a point on L. It doesn't matter where the point is on L. There are infinitely many points on L. We can pick any of them. So let's just pick a value that makes it easier on us. So it can be anywhere. So let's choose when z equals 0. And again, this is for ease. So it's so that we're making it easier on ourselves. So we're saying, what about, I know there will be a point when z equals 0. So what point is it when z equals 0? If we go about it this way, we can take these equations, plug in z equals 0 into both of those. So we get x plus y equals 1. And x minus 2y equals 1. And we can go ahead and solve that. We end up getting x is 1 and y is 0. That is the only solution to that system of equations. So we have x is 1, y is 0, z is 0. So 1, 0, 0 lies on L. And again, it didn't have to be that point. You could have picked a different value and found a different point. Again, there's infinitely many to choose from. Now, the tricky part is figuring out the direction vector. Okay, so for the direction vector, we need to know what direction L is pointed. We know that it lies in both planes, right? So it lies in this plane and it lies in this one. This is where the relationship with the normal vectors comes into play. Okay, since L lies on this plane, it must be orthogonal to N1. And since L lies on this plane, it must be orthogonal to N2, right? L is on the red plane, so it's orthogonal to this. It's also on the blue plane, so it's orthogonal to this. Okay, because it's in both. So because of that, we need a vector that is orthogonal to both N1 and N2, and we can create a vector that's orthogonal to them by crossing them together. So we can cross N1 with N2. The result is orthogonal to both of them, just like L is. Okay. So let's go ahead and write this out here. So since L is on both planes, it is orthogonal to N1 and N2. Thus, L is parallel to N1 cross N2. So to get our direction vector, so V, we're going to cross N1 with N2, so that's 1, 1, 1, and 1, negative 2, 3. Run that cross product, we get 5i minus 2j minus 3k. All right. So let's see, what were we looking for? We're looking for the symmetric equations for this line. We now have a point on the line, that's r naught, right? So that's x naught, y naught, z naught. And we have our direction vector, so that's the a, b, c. So we can go ahead and create those symmetric equations using any of the means we've talked about before. So you can like set this up using the vector equation, convert it to parametric, and then convert it to symmetric. Or if you just remember the general form of the symmetric equations. So we get symmetric equations. Remember, that's x minus x naught over a equals y minus y naught over b equals z minus z naught over c. So we're going to get x minus 1 over 5 equals y minus 0, so just y over negative 2, equals z, also minus 0, over negative 3. And those are the symmetric equations of the line of intersection between those two planes. So we're kind of bringing it all together in this example so we can try to, understand the relationship between the planes, both numerically and graphically. We can then understand the relationship between the line and the normal vectors. We can look at the equation of the line and see how that relates as well. We had some cross product in here as well, and some dot product as well in part A. So A really good kind of all-inclusive example here. But that brings us to the end of section 12.5. I know this was a pretty long one, so thanks for sticking with it all the way through. The next couple sections are going to be a lot shorter than this, I promise. Good luck with the upcoming assignments, the upcoming lectures, and I will talk to you all very soon.